My name is Kenji Fujii. This time I would like to make a presentation entitled Application of the Pushover-Based Procedure to Predict the Largest Peak Response of Asymmetric Buildings with Buckling-Restrained Braces. It is well known that asymmetric buildings are vulnerable to earthquakes. This is because excessive deformation occurs at the corner columns due to unfavorable torsional effect, and which leads to premature failure of members and collapse of the whole buildings. For the seismic rehabilitation of asymmetric buildings, using energy dissipative damper is one promising choice. From the past analytical studies, it has been shown that the unfavorable torsional effect can be reduced by installing of hysteresis or viscous dampers. However, there are some problems. The one is, in most of past studies, asymmetric buildings are assumed to have linear elastic behavior. So, more investigation on the nonlinear behavior of asymmetric buildings with dampers are needed. In recent years, the pushover-based simplified nonlinear analysis procedure, which is often referred to as the nonlinear static procedure, have been extended to asymmetric buildings by some researchers. It will be valuable if these extended versions of the nonlinear static procedure were applicable to asymmetric buildings with dampers. However, there are problems. One critical problem is, in most of these studies, torsional effect is estimated from elastic behavior. In case of asymmetric buildings with dampers, especially reinforced concrete buildings with hysteresis dampers, the mold shape may change notably in the nonlinear range. So, the estimation of the torsional effect based on linear elastic behavior would lead to notable error in case of asymmetric buildings with dampers. In 2014, the author has proposed a simplified procedure to predict the largest peak seismic response of an asymmetric buildings subjected to horizontal bidirectional ground motion acting an arbitrary angle of incidence, which is presented in the Bulletin of Earthquake Engineering. This proposed procedure is one of the extended versions of the nonlinear static procedure, and it considers the effect of the change in mold shape and bidirectional excitation. So, this procedure has promise for application to an asymmetric building with dampers. In this presentation, the applicability of the simplified procedure to reinforced concrete asymmetric buildings with hysteresis damper is investigated. Here shows the outline of this presentation. In the first part, the outline of the simplified procedure to predict the largest peak response is explained. In the second part, the building and ground motion data are shown. In the third part, the comparisons of the predicted results with time history analysis results are made, and the accuracy of the simplified procedure in case of asymmetric building with and without dampers are discussed. In the first part, the effect of the change in mold shape on the accuracy of the nonlinear static procedure are discussed. So, the outline of the simplified procedure to predict the largest peak response is explained in detail. This simplified procedure consists 5 steps. In step 1, pushover analysis of a frame model is carried out to obtain the force displacement relationship representing the first mold response. In this pushover analysis, the change in the first mold shape is considered. In this study, the displacement-based mold adaptive pushover analysis, which is developed by the author, is carried out, and then the property of the equivalent single degree of freedom model representing the first mold response is determined. Note that the direction of seismic input considering the first mode response, which is referred to as the principal direction of the first mode response, is determined based on the first mode shape in each step. In step 2, the peak response of the equivalent single degree of freedom model representing the first mode response is predicted by the equivalent linearization technique. As shown here, the intersection point of the capacity curve and demand curve represents the predicted peak response. In step 3, another pushover analysis is carried out to obtain the force displacement relationship representing the second mode response. Based on the results of steps 1 and 2, the second mode vector is determined in terms of the first mode vector at predicted peak response of the first mode. From this result, the property of the equivalent single degree of freedom model representing the second mode response is determined. In step 4, the peak response of the equivalent single degree of freedom model representing the second mode response is predicted by the equivalent linearization technique. Note that as the demand curve, the response spectrum of the major component is used. That is the same as step 2. In step 5, the largest peak response at each frame is predicted by the combination of 4 pushover analysis. From the results of steps 2 and 4, 4 combined force distributions are determined by these equations. Then the 4 pushover analyses are carried out. The predicted largest peak responses are obtained as the envelope of 4 pushover analysis results. Next, the buildings and ground motion data is explained in detail. In this presentation, the results of the 2 building models are shown. One building is model O, which is the model without dampers. This building model is 4-story building model with bidirectional eccentricity. Each frame structure is designed according to strong column weak beam concept. Sufficient shear reinforcement is provided to all members to prevent shear failure. Another building model shown in this presentation is model BRB28, which is the model with buckling-restrained braces in frames Y4 and X6. In these frames, the same buckling-restrained braces are installed. In this study, the 2-in-2 buckling-restrained braces are used. In this study, the seismic excitation was considered as bidirectional in XY plane, and 3 sets of artificial ground motions are generated. The shapes of the target spectrum is assumed to be the same in both major and minor component. In this study, the target spectrum of the minor component is reduced by the parameter gamma. Here the parameter is set to 0, 0.5, 0.7 and 1.0. In this study, the direction of seismic input varies with interval of 15 degrees. Next, the predicted largest peak response is compared with the time history analysis results. In this study, the predicted results are compared with the envelope of dynamic analysis of various directions of seismic input in case of gamma equals to 0, 0.5 and 0.7, while in case of gamma equals to 1.0, the average of dynamic analysis results are compared to the predicted results. First, I would like to show you the results of the asymmetric buildings without dampers. This figure shows the comparisons of peak roof displacement obtained from dynamic analysis and simplified procedure. As is shown here, the distribution of the predicted peak response at roof approximates the upper bound of the dynamic analysis results. This figure shows the comparisons of the story drift at frames y1, y4, x1, and x6. As is shown here, the predicted peak story drift agrees with the upper bound of the dynamic analysis except frame x1. Next, I would like to show you the results of a asymmetric building model with dampers. This figure shows the comparisons of the peak roof displacement obtained from dynamic analysis and simplified procedure. As is shown here, the distribution of the predicted peak response at roof approximates the upper bound of the dynamic analysis results. And this figure shows the comparisons of the story drift at frames y1, y4, x1, and x6. As is shown here, the predicted peak story drift agrees with the upper bound of dynamic analysis. Note that the results obtained for another model can be found in these proceedings. From this result, the simplified procedure can be applicable to asymmetric buildings with hysteresis dampers as well as those without dampers. Next, the effect of the change in mode shape on accuracy of the nonlinear static procedure is discussed based on the results of two building models. In this part, another prediction is made by using invariant mode shape. In other words, the peak response is predicted by using elastic first and second modes. This figure shows the comparisons of the peak roof displacement of model O, the building model without dampers. The plot variant is the result considering the change in mode shape, while the plot invariant is the result using elastic mode shape. As is shown here, the effect of the change in mode shape to predicted results is negligibly small in case of the model without dampers. This figure shows the comparisons of the peak roof displacement of model BRB2H, the asymmetric building with dampers. As is shown here, the effect of the change in mode shape to predicted results is significant in case of model BRB2H, the model with dampers. And the predicted results underestimate the response at frame x1 in case of invariant mode shape. To investigate the effect of the change in mode shape in both models, the first mode shape in elastic range and at peak response is compared. Note that the first mode shape at peak response is obtained from pushover analysis results. As is shown here, the difference of the first mode in elastic range and peak response is negligibly small in case of model O, the model without damper, while in case of model BRB2H, the model with damper, it is very significant. Here shows the comparisons of the property of equivalent single degree of freedom model representing the first mode response. The comparisons of capacity curve of model O is shown in the left and that of model BRB2H is shown in the right. As is shown here, the difference of the predicted results is negligibly small in case of model O, the model without dampers. On the contrary, the difference of the predicted peak is significant in case of model BRB2H, the model with dampers. In this presentation, the applicability of the simplified procedure to reinforce concrete asymmetric building with hysteresis damper is investigated. The results show that the simplified procedure presented by the author is applicable to asymmetric buildings with hysteresis damper, and the effect of the change in mode shape may be important in case of asymmetric buildings with hysteresis dampers. This is the end of my presentation. Thank you for paying attention.